In this video, we're going to discuss the size trends of atoms and how the periodic table and electron configuration helps us see that. To put it short, your atoms are going to get smaller as you move to the right on the periodic table in any row. And your atoms are going to get larger as you move down on any column of the periodic table. If we look at lithium, sodium, potassium, well, we could imagine their sizes. We could say here's lithium, sodium will be a little bigger, potassium will be a little bigger, rubidium will be a little bit bigger. As you go down a column, you get larger. What's going on with that one? Well, you're just a little further away. Your 1s orbital is a certain size, but your 2s is a little bit bigger. And your 3s is a little bit bigger than that. They have to go out farther. They can't take up exactly the same smaller inner space because then they'd need a wavelength that fits that space. So they have to go bigger to adjust for more nodes and have a larger overall size. And as a result, they have to take up more space physically out. When we think of the size of the atom, we're always thinking of the valence electrons, the outermost electrons for that atom or element or ion, whatever we're looking at. As a result, this is why the atoms look bigger. You're always looking at whatever your last orbital to be filled is, and going down from lithium to sodium and potassium, we are moving that further and further out into larger and larger s orbitals. As you move to the right on the periodic table, you'll get smaller. So we'll start reasonably big for lithium, we'll get a little smaller for beryllium, we'll get a little smaller for boron, and then for carbon and nitrogen and oxygen and fluorine. We'll taper down as we go to the right. What's going on there? Well, we're in the same shell. We're still in the same n equals 2, and so as we move across, well, we have a little variance for s and p orbitals. The general idea is we're not shooting way out to get to a new shell. Well, as you go from right to left, your z effective gets greater. And so if I have something with a +1, and there's an electron on the outside, it's attracted enough to pull in a little bit. But if I have a +2, that same electron, well, it's just more attracted. It gets a little bit closer. As you get a +3, well, that electron gets a little bit closer. The more charge there is, the more they pull in towards the nucleus, the smaller you can make your orbital. So by the time you're over at fluorine with a Z effective of +7, those electrons have pulled in quite a bit. The greater nuclear charge that they observe allows them to pull in closer to the nucleus. The net result is that the outermost electron is just not as far from the nucleus on fluorine as it was on lithium. And this is true for all the other rows as well. Sodium to chlorine, you're going to see the same size trend. Potassium to bromine, you're going to see the same size trend as you go across. As you move to the right, you just get smaller because your electrons are more attracted to the nucleus. This also plays in when we think about ions. So in previous video, we discussed that sodium, lithium, potassium all like to make +1 ions because that's when their electron configurations look like the last noble gas. Their shell, that is the outer side edge, is the previous shell, so the Z effective is much greater. You can't really make a sodium +2 because it's so attracted to its nucleus for that second electron. But the first electron leaves fairly easily. Well, by dropping down to an earlier shell for sodium, we had our 11 protons. You had your 1s's, you had your 2s's and 2p's, you had your 3s's. As soon as that electron leaves, well, the only ones that still have electrons in them are the lower shell, and so our outside edge drops from what would have looked like a radius like this down to a much smaller radius that looks more like that. Your cations get smaller. That's what we see here in our table. A neutral sodium atom has a radius of approximately 186 picometers, where a sodium cation has a radius of approximately 102 picometers. Now, radius is a little difficult to describe exactly. It depends on the type of bonding, which we'll discuss more in Chapter 9. But short version, if you have a metal, your two metal atoms are assumed to just kind of butt up next to each other. As a result, it's really hard to see the electrons, but it's not too hard to see the nuclei. So we'll measure this, we'll cut it in half, and we'll say whatever half the distance between nuclei, that's the radius. And so we'll call that the radius for an element. So for sodium, we would have had two sodiums. It would have been 186 here and 186 here for two sodiums. So it would have been, what would that be? 372 picometers between the two nuclei. Problem comes up if you have covalent bonds, more organic, things like carbon to hydrogen. Because instead of being at their edges, we'd think like this: covalent bonds overlap. They work their way into each other. And so we'd still find the nuclei, and we'd still say, well, what's half the distance between them? Problem is, when we see this with things like Cl2, if I have two chlorines together, you'll have two of them that overlap, but then you'll also have the neighboring two that, while overlapping with each other, do not overlap with the other one. And so you'll have one distance between the nuclei, but you'll have a different distance between unattached nuclei. This is where we can get the radius for a covalent atom much easier because, well, if we were to measure this one and cut it in half, because covalents overlap, it's hard to figure out what their radius is. But they only overlap with a particular atom. They don't overlap with nearby molecules. And so we look for the longer of the two distances and we cut that in half. And so in theory, it should be a lot like metals, but there's just a little bit of extra confusion and work that has to go into identifying the size of certain elements. As a result, occasionally some of them don't quite seem to fit the trend, but they tend to be because they were measured by using a different method. As we look, though, we can see the size trends as we go down. Lithium to sodium to potassium to rubidium, we get larger and larger. And even the cations are still larger as you go down, but they're always smaller than the neutral element was. If we look at magnesium versus sodium, the neutral, 160 versus 186. Magnesium was smaller, which makes sense. It has a +2 for its Z effective. Its orbital should be drawn a little bit more in. It also makes a +2 ion, and that +2 ion is a lot smaller than the +1 for sodium, despite having the same electron configuration. Magnesium 2+ and sodium plus both look like neon. They both have exactly the same 1s2, 2s2, 2p6. So why is magnesium smaller? Well, it still has a greater Z effective. There's one more proton in its nucleus, so its 2s and 2p orbitals see one more attracted charge. We go over and look at our anions. What we see is that they get bigger. Neutral fluorine versus neutral chlorine. We go from 72 up to 100. And then neutral bromine, 114, neutral iodine, 133. As we go down the column, we get bigger, which is what we expect. The negative ion, however, is larger than the neutral atom. What's going on there? Well, while we said it doesn't really change the Z effective to add one more electron to fluorine, that is still one electron who has its wave function, and the wave function does put a little bit of its negative near the nucleus, pushing everything else away. Remember our shape of our wave, you've got percentage and radius. In the electron, in the 2p, does have some percentage that's on the inside of, say, the 1s or the 2s. And so adding one more electron to the p orbitals does put a little bit of probability in here, so it will push all the other electrons a little away. The net effect is it gets bigger. If you just shove more stuff into a container, the stuff gets spread out. Putting that extra negative charge in kind of pushes on all the other ones, and they spread out to make space for it. An anion is larger than the neutral element. And we can see here fluorine almost doubles. The other elements aren't quite as drastic, but it's a rather significant change. So these are common trends that we will see for size of neutral atoms or cations or anions.